Okay, let's make a start. So last week we got up to, we did show that, looking at so before we made a two-port model in the Laplace domain. Okay, now we're going to look at the frequency domain. And again, in the frequency domain, we showed that indeed there were these forward and backward traveling waves, okay? And, the voltage and currents for the forward and backward traveling waves had these, relationship between the V and I given by Z0 or minus Z0, okay? So we did that last week, okay? So we're going to use that information now to create another way to solve for transmission line problems in the frequency domain, this time in the frequency domain. Okay, so now we're going to effectively, so say we have a source which has an ideal voltage source. It has an impedance to that source, and we have a transmission line of length L, and we have a load, okay, with an impedance ZL. What we're going to do is create a Thevenin equivalent model for the transmission line and the source, okay? So, we need to find this equivalent impedance, ZSC, and equivalent Thevenin equivalent voltage, Thevenin equivalent impedance of that transmission line plus the real source. And then once we have that, okay, we can just solve for any V, L, and IL at the load, okay? So we can solve for all the currents and voltages in the circuit, okay? So we need to first find this ZSC and this VSC, okay? So the way we're going to approach it is we have our piece of transmission line, and we label this x equals 0, and we'll label this x equals minus L, okay? And we have our ZL at this end here, okay? And we have, I at x equals minus L going in, okay? And we have I at x equals 0 going out into the load, and we also have V of x equals 0 here, and we have V of x equals minus L there. And again, we know that that V of x is given by the two traveling waves, okay, at any point in the line, okay? So we have V of x equals minus L is going to be V plus e to the plus j beta L now, because we're looking at position minus L, okay, plus V to the minus e to the minus j beta L, okay. And then we also have I of x equals minus L is going to be, related to V plus and V minus by, 1 on Z0 or 1 on minus Z0, okay? So it's going to be equal to 1 on Z0, V plus e to the j beta L, minus V minus e to the minus j beta L, okay? Okay, so okay? So, sorry, this is meant to be ZS, okay? So we're trying to find, we want to find the Thevenin equivalent impedance, okay? So we're going to remove, so we want to look in here and effectively transfer this ZS to the load, okay? So do that, we take off, or we just try and get the Thevenin equivalent of this circuit, okay, as seen by the load. So we're going to take off the load, of course, and we're going to remove the independent voltage source, VS, and just put ZS there, and we want to find what the impedance we see looking in, okay? So that's what we've done here, except we've just changed the coordinates a little bit, okay? So we're looking at, so x equals 0, we put ZS, and x equals minus L, it's where we're looking in, okay? So we're looking in ZSE like that, okay? Okay, so obviously ZSE is going to be, Vx at x equals minus L on Ix at x equals minus L, okay? Okay, so is that clear? Now, we can also look at, so that gives us some ratio of V plus and V minus, okay? If we put that like that. But we need a little bit more information, okay? So where can we get that bit of extra information? We get another equation to anywhere? Where would you be? Anyone? So if we look at ZS, okay, so it says something about, do we know anything about the relationship between Ix and Vx at x equals 0? What is it? What's the relationship between the two?
V at 0.
Exactly. Okay. Exactly. Okay. So we know that V at x equals 0 on I of x equals 0 equals ZS, right? Okay. And we know what V of x at x equals 0 is V plus V minus, right? Because you put 0 instead of L there, and it just becomes 1. Okay. So it's going to be okay. So we've got that's going to equal Z0. Okay. V plus plus V minus on V plus minus V minus. Okay. Okay. Because the relationship between I of x equals 0 equals 1 on Z0 outside of V plus minus V minus. Okay. Yeah. Okay. So that gives us another equation. Okay. So we can manipulate that equation a little bit. So we can go multiply this out. We'd get ZS V plus minus ZS V minus equals Z0 V plus Z0 V minus. Is that right? Okay. And then we could get the V plus and V minus together, so we can get ZS minus V0 V outside of V plus equals ZS plus Z0 outside of V minus. Okay. Okay. And then if we get the ratio of V minus on V plus, okay, that's going to be equal to what's it going to be equal to? ZS plus Z0 on ZS minus Z0. Is that right? No, it's the other way around. Sorry, it's plus and this is minus here, right? Okay, is that right? Yep. Okay. And we call that something special. Call that rho the reflection coefficient. So that rho gives the ratio of the backward travelling wave to the forward travelling wave. Okay. Okay. So it's what we use that to find. If you have a forward wave and hits the end, then it gives you the ratio of what the backward travelling wave will be. Okay. So it's quite an important thing. Okay. So if we look at what this ZSE is up here, it's going to be Z0 outside of V plus e to j beta L plus V minus e to the minus j beta L on V plus e to j beta L minus V minus e to minus j beta L. And if we divide through by V plus both top and bottom, okay, it's going to be something like Z0 e to the j beta L plus we're going to have V minus on V plus. Okay, so that's going to be rho e to the minus j beta L on e j beta L minus rho e to the minus j beta L. Okay, so you can see we've managed to find ZSE. Okay, so it's now that's just in terms of what the characteristic impedance of line is and ZS and something to do with the length of line. Okay, is that clear? So you can use simplify that a bit. If you use Euler's equation, I think e to the j beta L equals cos beta L plus j sine beta L. Okay, and rearrange it, and you end up with I think ZSE equals Z0 ZS cos beta L plus j Z0 sine beta L on Z0 cos beta L plus j ZS sine beta L. Okay, so plus this, those two ends up something like that. Okay, so we found the Thevenin equivalent impedance. Is that clear? Okay, and you don't have to remember that. I mean, I go through this so that at least you see how it comes about. Okay, so you can see here in your formula sheet that you're going to get in any quiz or exam. It says transfer of impedance Z from x equals L to x equals 0 to x equals L. A lossless transmission line frequency domain is given by this. Okay, is that clear? So you can always, you don't have to remember the formula, but I'm trying to just show you how we get there. Okay, is there any questions on that so far? Okay, so we've done one part. Okay, next part we need to get the Thevenin equivalent voltage. Okay, so we've got our line here. Okay, we've got ZS. Okay, and we've got VS, and we need to find the Thevenin equivalent voltage VSC. Okay, we've got VS dash. Okay. So and this is an open circuit. So so the approach will be we'll try and find this voltage here, VS dash first. Okay. If we can find VS dash, okay, then we'll look at how we can transfer that to the end of the line. Okay. So the first thing to find VS dash, what do we got to find? What would we want to find VS dash? So what would we do next? Sorry? Yeah. Okay. So that's right. So what we really need to find is ZS. We need to find some equivalent load here, or ZL, that corresponds to that open circuit piece of transmission line. Okay. Sorry. Yeah, we use KVL, right? Yeah. So eventually we'd find VS dash is going to be we'll just call that ZL for the moment. I might call it ZL dash. I don't know. It's going to be VS times ZL dash on ZS plus ZL dash, right? Okay. So we got to find what does that piece of looking in here, and we've got this is an open circuit. And we put this at x equals 0. Okay, x equals minus L. We've got to look in here and see what this ZL dash is. Okay. So what can we say about the impedance at this point? Anyone? It's infinite, right? It's infinite. And could we use a result that we've just found to find what ZL dash is? Anyone? How would we find ZL dash? Is there anything we've been looking at that would tell us what ZL dash is? Anyone? No? Okay, so we just looked at this situation where we had ZS, right? And we're looking in here and finding what is the impedance seen. Okay. But now if we just substitute infinity for ZS, don't we get exactly what we want? We're going to find out. Is that right? Yeah? Okay, so we can see that the ZL dash is going to be Z naught outside of whatever remains here when ZS tends to infinity. Okay, so if ZS tends to infinity, okay, these terms here and there are going to disappear. Okay, so it's just going to be Z naught outside of cos beta L divided by J sine beta L, right? Is that right? Yeah. Okay, cos beta L on J times sine beta L. Okay, so that's something we can use in the future. Okay. Is that clear? Okay. So, and from that we could find, we can find what VS dash is. Okay. Now we need to find what the VSE is. Okay. So, we've got VS dash here, and then we've got what we want to find is VSE. Okay. And we say x equals 0. This is x equals minus L. Okay. So we know at this point we've got Ix equals 0. Okay. Because remember we've got infinite impedance here. Okay, so remember, whenever you put something on an element on the end of a transmission line or on anything else, the VI relationships are forced to obey this particular element. In this case, the element's an open circuit. That means that the current going through that element always has to be equal to 0. Okay, if it was a short circuit, it means that the voltage across it would always have to be 0. Okay, so we've got VSE, and that's actually at Vx is what Vx is at x equals 0. Okay, and we know, look here, that's going to be equal to V plus V minus. Okay, and then we also had this other relationship between because we know that Ix at x equals 0 equals 0, then we know that 1 on Z naught V plus minus V minus has to also equal 0. Okay, so this implies, what does that imply? If that's true, anyone? If Ix is at x equals 0 0, it means that 1 on Z naught V plus minus V minus equals 0. So if Z naught's not equal to 0, or not equal to infinity, then it means that V plus equals V minus. Okay. So we can say that VSE is going to equal 2V plus. Okay, that's what it's going to be. Okay. Now we go back to the other end of the line. We know that VS dash, okay, is equal to it's V plus e to the J beta L plus V minus e to the minus J beta L. Okay. And we found that we know that V plus equals V minus, okay, and we know that VSE equals 2 times V plus, okay, so we can substitute those into here to get VS in terms of VSE, okay. So everyone following this? Okay, so let's do that. So VS dash is going to be VSE on 2 outside of e to the J beta L plus e to the minus J beta L, okay. And this, we can use Euler's formula. I think it comes to 2 cos beta L, okay? That's what that is going to be. Okay, so, and we found VS dash up here, okay? So we found VS dash, so we can bring that together. Let's see what we get. So we've got VS ZL dash and ZS plus ZL dash equals VSE cos beta L, okay? So VSE equals ZL dash on ZS plus ZL dash 1 on cos beta L times VS, right? And we found that ZL dash is given by this, so we will have VSE equals Z naught cos beta L on J sine beta L divided by ZS plus Z naught cos beta L on J sine beta L times 1 on cos beta L times VS, so that should cancel there. Okay, and if we times top and bottom by J sine beta L on J sine beta L, we'll get it's going to be equal to Z naught times VS divided by ZS J sine beta L plus Z naught cos beta L. Okay, so that's VSE. Okay, and that's what you get. Okay, you can see here on your formula sheet you get that. Okay, so now we can see that we've got both, the ZSE, okay, because remember we initially were able to find, we're able to transform the impedance at the source to what we'd see at the load, okay, after going through a section of transmission line. Okay, we've found that, and if this was an open circuit, okay, we found now this VSE, which is what the Thevenin equivalent voltage of that system looking back in this way. Okay, so we found those two things. Okay, so then once we've got that, we can solve for any of the unknowns. in the circuit. So we can solve for VL and IL given a particular load. Okay, is that clear? So these are what we just saw. Now we will use that probably. I'm not sure we'll get to it this week, but it's quite a good chance we'll get to that this week, and we will actually make use of that to solve for specific problems. Okay, that are fairly relevant to high-speed integrated circuits and stuff like that. High-speed printed circuit boards. Okay, so any equivalent? Any questions on that? Anyone? Do you find it useful in trying to understand that we go through these, that we work through this, and you see how it all comes about? Yeah. Okay. So that's freaking. So in that way, we've made instead of having a two-port model, we've made some other sort of model of a transmission line, which we can use to solve for any unknowns in the circuit. Okay. So we could also do something similar in the Laplace domain. Okay. So we could use we could also have done that from the Laplace domain. I think it just goes through it. Okay. What we've just done then. Okay. So this is just going through what I went through then. Okay. It's just in the notes. Okay. Okay. And we end up with whatever we get. Okay. And this is if we wanted to find VL. Okay. Then this VL is just going to be VSE times ZL divided by ZSE plus ZL, and that's what we got here. Okay, so now we could also do something similar in the Laplace domain. Okay, so we could find Laplace domain the Thevenin equivalent impedance and voltage for a section of transmission line with a source impedance in the Laplace domain. Okay, and we could do that using the actual two-port model that we already have, because we already have a two-port model for the Laplace domain for a transmission line, so we could use that. Okay, it's another way of looking at boundary conditions and using two-port models. Okay, so in the Laplace domain we have VS, we have ZS, and then we have the actual two-port model of the transmission line given by this ABCD matrix. Okay, by transmission matrix. Okay, oops, sorry about that. Okay, so and we have, what do we have? We have I1 of S going in like this, and we have V1 of S across the input, and the output we have V2 of S, and we have I2 of S. Okay, and the ABC, and just note be careful about the signs here. Okay, so in your sheet you get given V2, this matrix with respect to V2 and minus I2 of S. Okay, so if you were to use it, if you wanted V2 and I2 of S, then both these terms have to have a negative in front of them. Okay, so just keep that in mind. Okay, so we have V2 I2 is related to this ABCD. Okay, V1 I1. Okay, so if we want to find the open circuit voltage, okay, what would we do? I mean, we want to find the Thevenin equivalent of that, so we'd want to find V2, this V2 of S, okay, with I2 being 0. Okay, so then we could say we get a set of equations. Okay, we multiply it out. Okay, we get V2 is going to equal A times V1 plus B times I1, and we get 0 equals CV1 plus DI1. Okay, and we could eliminate I1 from this equation. Okay, by using this one, so we can see that I1 equals, what is it, minus C on D times V1. Okay, so we get V2 AB1 minus CB on D V1. Okay, so it's going to equal AD minus CB on D V1. Okay, so that gives us one sort of constraint, or one equation. Do we have information about on this side? So if you might remember, some of you did ELEC4401, NASC4021. Someone who did that here, and we looked at just this sort of problem. Okay, and having a two-port model and having constraints on either side of the two-port model. Okay, so we can get another condition. Okay, so we can get V1 can be expressed as also V1 and I1 have to satisfy also some conditions. Okay, so what will V1 and I1 satisfy? Anyone say anything have to satisfy? Anyone? Sorry? I can't hear you, sorry. Okay, yeah. So that has to be, if we do, like KVL around that loop. Okay. So, V1 equals Vs minus Zs I1, okay? Okay, so we could get, you see here we've got an equation for I1 and V1, okay, so we get V1 equals Vs minus Zs V plus, okay, plus C on D V1, so we get V1 outside of 1 minus Zs C on D equals Vs, right? Okay, and then so V1 would equal Vs times D on D minus Zs C, okay, so upside down. So then this could go into here, okay, and then we'd have we get V2, which is what we want. So we want the V2 is going to be our Thevenin equivalent voltage, right? Okay, V2 is going to be A D minus CB on D minus ZSC times Vs. Okay, is that clear? And then check it's right. It is indeed. So you can see that we've just got the Thevenin equivalent voltage. Okay, and you could substitute in. So on your sheet, this is A, this is B, this is minus C, and this is minus D. Okay, so you have to put a minus sign in front of them, but that will give you the Thevenin equivalent voltage now. Okay, and you can see also that it doesn't matter in this particular case. It doesn't matter if what the sign of I2 was, because it was 0, right? And you can see even if you didn't have C and D minus, you still get the same result. Okay, because that minus sign cancels out. And that's because you chose I2 to be 0 in this case. Okay, so that wouldn't have to worry too much. But when we come to the next one, you have to be careful about the signs. Okay, so we eventually find this. Okay, and when you plug it in, this is what you get. Okay, you put all those ABCD values in, you'd get this. VSE divided by Vs is given by this. Okay, or VSE equals Vs times this factor here. Okay. So now we need to find. We found VSE. Okay. We need to find the equivalent impedance, right? So we need to find what the source impedance looks like when you remove the Vs, okay, and you're looking in from the far side of the transmission line. Okay, so that circle would look something like this: A, B, C, D. Okay, and then we will have Zs. Okay, and we've got this is V1 of S. Okay, and this is I1 of S. This is I2 of S, and this is V2 of S. Okay, now in this case, I2 of S is not 0. Okay, what we need to find, we want to find ZSE. Looking in there, sorry about that. We want to find ZSE equals V2 of S divided by I2 of S. Okay, that's what we want to find, that ratio. Okay, and that's going to give us what ZSE is. Okay, and so we've got the equations. We've got V2 equals A times V1 plus B I1. I2 equals CV1 plus D I1. Okay, so we've got some other constraint on this side of the 2-port. Okay, and that constrains I1 and V1 to be related by Zs. Okay, so once we put the load there, we get a relationship between I1 and V1. Okay, so and that is going to be V1 and I1 equals what will be with the definitions of I1 and V1 like that. What's V1 and I1 going to be? Zs, you reckon? It's minus Zs. Okay, it'll be equal to minus Zs. Okay, and it's minus because the way we've defined I1. Okay, so if V1 is a positive voltage, okay, then current's going to flow in this direction, won't it? Okay, but that's in the opposite direction to what I1 is. Okay, so V1 on I1 will be minus Zs. Okay, so maybe we'll just stop it there, and we'll finish that off next lecture. Okay, and so so I think the next people will come in. So is there any questions on that? Yep. We'll look at it. So any situation you're going to have, we will look at some examples, actual practical, quite useful examples. But you could, once you've got all these equations set up, you should be able to solve any problem with the transmission line.